The speaker is Professor Hao Zhou from CIMMYS and Fudan University. He's going to talk about counting Bethe states in twisted spin chains. Let's welcome.
Yeah. Okay. Thank you for the introduction, and thank the organizer to giving me this opportunity to share our recent works. As just introduced, I will talk about counting Bethe states in twisted spin chain. This talk is based on several works. These are joint works with Hongfei Shu and Peng Zhao and Ruidong Zhu. And I should point out that actually main results already presented in these two papers, in two physics papers, but we are writing a math paper to rigorously prove this result. Okay, so here is the outline of this talk. I will start with introduction about what are the problems we are going to solve, which is the completeness problem. To solve this problem, we are going to solve this problem in two steps. The first one, we will count Bethe states in the fully twisted spin chain, and then we are going to untwist the spin chain and give a counting formula to count all the Bethe states in all these twisted spin chain with various diagonal boundary conditions. So let's start with a brief introduction. Okay, let me start with Heisenberg spin chain. You may all familiar with, but please bear with me a few minutes. So let us consider a spin chain of length L, and let's for now just focus on spin 1/2. It is this picture depicts a periodic one, but later we will see it can be other twisted ones. But anyway, let's start with this most simplest one, XXZ spin chain with spin 1/2, and the Hamiltonian with a homogeneous nearest neighbor interaction is given by this one. And as we apply the periodic boundary condition, which is SL plus 1 equals S1, this actually implies the global symmetry of this spin chain, which is SU2. And we can choose a pseudo vacuum where all the spins point up, and the excited state would be where some spins flipped. And the number of flipped will call the Magnum number. So in 1931, Hans Bethe has already found a way to find the eigenstates for this excess spin chain, which we now call the Bethe-Yanaz equation, which is a set of nonlinear equations take this form, where I will explain the parameter U's later. But nowadays, the original way Bethe derived these equations are called coordinate Bethe-Yanaz. But now we have the Faddeev school has developed the so-called algebra Bethe-Yanaz. We will also use it in the second part of this talk. Okay, so these eigenstates, these nonlinear equations determine these eigenstates have some parameter U, which is related to the momentum PA by this equation. And these U parameters are called the rapidities. And the eigenstates will take the form of this linear combination, where the F is actually taking the form of e to the I pi combinations with S matrix inside that. Okay, so as Faddeev and his collaborator actually derived that all the Bethe states should be the SU2, since we have the SU2 global symmetry. So all the states are SU2 high-square states. Okay, previously we just introduced the most simplest example of XX spin 1/2 spin chain. And there are some generalizations. For example, we can generalize the spin 1/2 to more general spin, say spin S. And that means on each side, it's 2S plus 1 dimensional representation of this SU2. And as I mentioned, we can actually destroy the periodic boundary condition by apply this twisted boundary condition, where the twisted parameter is so-called Q, or you can also use the theta which is a twist, it is a theta angle. And if you apply this twist boundary condition, the global SU2 symmetry will break to U1. And this twist condition can be realized by imposing a magnetic field. And there's another generalization by introducing the inhomogeneity. So we name it denoted by V alpha. So by these generalizations, the previous Bethe-Anders equation will become like this one. Of course, we can also generalize to more general global symmetries. For example, the higher rank global symmetry SUR plus 1. And this model is diagnosed by the so-called nested Bethe-Anders, which was originally proposed by Yang in a very famous paper. Then in this case, we have a set, multiple nonlinear equations taking this form. And we can also study the supergroups like considering the TJ model, or we can introduce impurity like the Kondo model. But our methods introduced in this talk also applied to these two models, but I will skip for this talk. Okay, so what is the problem we are going to solve? It's so-called the complete problem, which asks the following question. So basically, we can solve this nonlinear equation, but whether all the solutions of this Bethe-Anders equation give you physical Bethe states. This is a non-standing problem starting from the very beginning since Bethe pointed out. And to solve this problem, basically, we need to count the number of the so-called physical Bethe states. And there are some several solutions. For example, Kirnov and Kirnov-Reshtikin has proposed a solution in the 80s and 90s based on string hypothesis. And there are some conjecture in 2013 by Nepomniachtchi's group. They have some conjectures based on numerical study and also detailed study of the singular and repeated solutions to this Bethe-Anders equation. And also there are some people developing numerical techniques to directly solve this nonlinear equation, like starting from, for example, Borning and also Yuanfen Zhang's group. Okay, so previous I mentioned some singular and repeated roots. And the singular and repeated roots will cause some problem on the so-called physical condition. For example, if you take the singular solution, which means the UA equals to plus minus of I over 2, this equation will have infinity, and that will change the physical condition. And you need to take care of this. The solution will, the equation will become differently. And so same thing happens when you consider the repeated roots when UA equals to UB. And of course, in this case, or for higher rank cases, the discussion of singular and repeated roots are still missing. However, the above subtleties can be resolved if we turn on generic twist boundary condition. For example, we can in these papers, if you turn on, they discuss if we turn on the twist boundary condition, the previous singular solutions will be regularized by a small amount epsilon. So based on this observation, we will count the Bethe states in 2 steps. One is we start from the fully twisted spin chain, and then in the second step we will restore the periodic boundary condition. Means we will restore the full global symmetry by turning off this twisted parameter. And more specifically, the first we will use the Bethe gauge correspondence to solve the first step. So in this step, instead of directly solving the Bethe equation, we will calculate the Wnt index, and in the second step, we will use some techniques from the representation theory to find all the states that are left when we turn off this experiment. Okay, so I will go with the first step, which by introducing Bethe gauge correspondence. Okay, before that, let me give a review of the GSM, so-called the gauge linear signal model. The key ingredients to define a gauge linear signal is we have a gauge group, and we have a bunch of matter fields under certain representation of this gauge group G. We have vector supermultiplied and the superpotential, and we also have a twisted superpotential. Here, R is the Fi parameter, theta is the theta angle. As you may see, we use the theta, and this theta will correspond to the twisted boundary condition. Here is it's a real number parameter coupling to this vector supermultiplied. Oh, you mean the names? Okay, so F stands for, sorry, I don't know how to pronounce it. Fayette, yeah, right. And the Lagrangian for this theory is given by the kinetic terms for the matter fields and the gauge fields. We have the superpotential terms and the twisted superpotential terms. And we also have a global symmetry like flavor symmetry and R symmetry. The flavor symmetry, we will use the flavor symmetry to turn on the background twisted masses, which will play an important role later. Oh, sorry. There's some picture missing. I don't know why. It seems, yeah. Okay. I'm sorry about this slide, but there should be some picture inside. I can draw. Actually, we are interested in the vacuum of the GSM, which is determined by the scalar potential. Essentially, it is determined by the so-called D term and F term. I'm sorry, it didn't show up, but this vacuum is determined by the scalar potential, which denoted by U. A typical vacuum will look like you have a bunch of branches, like depending on the expectation value of this matter fields or gauge fields, and the so-called Higgs branch or Coulomb branch. I'm sorry about this. But it's more easier to start with a toy model. This is GSM for CP1, CP(n-1), which is defined by gauge group U1, and it has n chiral fields phi I with all the U1 charges 1. And this D term, in this model, we don't have the F term, we only have a D term. So the D term equation, it looks like this. If you solve this equation, the vacuum is determined by this D term equation. And if you look at the R greater than 0 phase, you can find a solution by this one, by this equation. And if we quotient this U1 the gauge degree of freedom, it actually gives you the CP(n-1), which is described this Higgs branch. And if you consider R less than 0 phase, it seems there's no solution to this D term equation. But as Witten argued, there's a quantum correction which will rescue, and the vacuum in this phase, in this R less than 0 phase, consists of pure Coulomb vacuum, which I will introduce now. And this Coulomb vacuum is actually determined by a single function called the effective twisted superpotential, taking this form, where the second term is one loop corrections to the effective twisted superpotential. The vacuum is determined by this equation of motion. You basically take the derivative of this superpotential and you will find out this solution is sigma to n equals to q. And one remark is on the positive phase, which is CPN minus 1, the Higgs branch is the projected space, where on the another phase where R less than 0, it's actually just the n point. And the wind index matches in different phases.
What is the difference between beta?
Mathematically, no, but yeah, the physical reason you need to go to a larger radius region. R is R basically the Keller parameter. Okay. And okay, I should point out that in this model, there's no singularity on the modular space, which is different with the model we are talking about, where they will have some singularity. Okay. As I mentioned, there's a flavor symmetry. In this model, it's SUN. So we can turn on the background gauge field with wave, we denote it by M alpha. And this model will, so in the IR, the effective theory will determined by this model, where we have the distant mass parameter appearing in this function. And the equation of motion will be modified by this minus M alpha. So, however, this is not the model we are considering later. What we are going to consider is determined by this quiver diagram, where the circle with M inside is denoted, the gauge group is a UM, and we have L pairs of fundamental and anti-fundamentals, and we also have a joint matter. And also we have a superpotential term, which taken this form. If we follow the previous procedure, we will find out the Coulomb vacuum equation will take in this form. And if you remember the x-axis spin chain, you will find out this equation actually appears both in a gauge theory on the left-hand side and also the spin chain side. So that is motivation. That is original story where Nekrasov and Chatashvili point out the correspondence between these two models. And since they share the same set of nonlinear equation. Okay, and more specifically, these are the more detailed dictionary between these two models. And the gauge group UM, where the rank of M match to the maximum number on the spin chain side, and the L pairs corresponding to the number of spins, and the theta angle here, theta, corresponding to the twisted boundary condition. And the twist mass will give you the inhomogeneity and the spin S. And the effective twisted superpotential on the left-hand side give you the Yang-Yang function. And as we just see, the Caroline relation on the left-hand side matches the Bethe equation on the right-hand side. And I should point out, I already let the FR parameter equal to 0 and keep the generic theta. And if you go to the theta equal to 0, that is a single point of the gauge theory, which on the left-hand side, we cannot use left-hand side the gauge theory to study this single point. Okay, so the lesson we can learn from the previous story is that the Bethe roots will one-to-one corresponding to the Susy vacuum. And so instead of solving the nonlinear equations, we can actually count the Susy vacuum from on the gauge theory side. So that can be done by compute the wind index, which is this partition function. And in fact, we compute the refined wind index, so-called the elliptic genus, which is takes this form and with more with parameter from the global symmetry, like R symmetry and flavor symmetry. And there's some advantages we compute this elliptic genus. One is there's a supersymmetric localization formula we can directly apply. And and also another advantage is that in Inequagenous, we can use Inequagenous to find its dual theory, like so-called Separate-like dual. Actually, we are working on this with some students to find to use this technique to find the Separate-like dual. And more importantly, we will see that the pole configuration will give you some combinatorial problem, and I will later show what's the combinatorial problem in the following. And there's a again I should emphasize that we need to keep the theta to be non-zero to avoid the singular point on the modular space. Yeah. Yeah, and also I already make the FR parameter to 0. So yeah, yeah. I already make the take the R equal to 0. Yeah. Okay.
Previous slide you say it's only between them. Same is for the spin area.
This one. Yeah.
Right side M is this side. This side.
Yeah, M is less than L. Yeah, yeah, M less equal to L. Yeah.
It means it.
Oh, that you can define the UL gauge theory.
My question is on the right hand side, you cannot take M greater than L.
No, yeah, this one you can also cannot take because if you calculate the wind index, that will give you 0. I mean, yeah, yeah.
If I take M greater than L, but
The wind index is 0. There's no substitution. Yeah, yeah.
I
What do you mean by? Yeah, up to a sign. Yeah. Yeah. Actually, we find out in the example we are going to see that there's no such sign ambiguity. We will find because we probably choose the pole configuration. All the numbers are positive and give you the answer on the spin chain side. Yeah. Okay. For example, like we can start with the SU2 as a spin chain, and the Inequagenous calculation will give you this this expression for the Inequagenous. And to get the wind index, you need to take the global symmetry parameters. Here, in this case, it's a R symmetry parameter Z go to 0. You will find out it's just a combinatorial. It's this number where the N alpha is less than the minimum of this 2S and M. And if you calculate carefully, we'll give this this binomial product, the sum of this binomial product. And however, you can use another way to express this one. Like it's actually a combinatorial problem by putting M blue box inside this L times 2S boxes. And we will denote this combinatorial result is as CSL of M. Similarly, you can calculate the SU3 and SUR plus 1. And the corresponding combinatorial problem is actually a 3D restricted combinatorial occupancy problem. We have different layers of boxes. We need to put R layers of boxes, M2, each layer on top of another one. And each layer will have blue boxes M1. And we will denote this result at the CSL with M vec. Yeah, yes. Okay, so luckily, since this is a combinatorial problem, we can write a we can solve it using combinatorial techniques, and we can extract this number from this generating function. Here, the S with 2S, it's a Schur polynomial determinant partition. It's a one-row partition of length 2S. You can extract this number by looking at this generating function. Okay, so far and actually we did some numerical test by directly solving the Bethe equation, we find this number matches. Okay, here is a quick summary. So far we can give you the Bethe states, the number of Bethe states of the fully twisted spin chain by computing the wind index, and the answer is given by this combinatorial problem. Yeah. Okay, so let's untwist the spin chain. So that means we need to take theta angle to 0. However, we don't know in the gauge theory side, because theta equals to 0 is a singular point on the gauge theory. At first, we did some numerical test by directly solving the Bethe equation when theta goes to 0. We find out that in the SU2 case, the original states, the number of states is CSLM, and when theta goes to 0, it's actually CSLM minus something, where the M is, the second term is M minus 1 instead of M. And we did this for the SU3, and we find out we need to minus this part. And we find out in the literature that Nippon-Biki already made some conjecture on this SU2 case. They conjecture that the periodic x-axis spin chain with SU2 globe symmetry, it should have this number of Bethe states. And from the gauge theory side, this number with red 9 under 9 corresponding to the states we need to subtract when we go to the singular point. And from the point of GSM, that means when we go to the singular point, there's some open flat direction open up in the scalar potential. Some discrete ground states will flow to the infinity. But however, we don't know how to analyze in the GSM purely from GSM. So, but we can actually use some representation result. Okay. Okay, this is numerical results we did. When we solve the Bethe with theta go to 0, we find out we need to subtract some number of states by this one, by this much. Get the number of physical Bethe states in the spin chain set with the periodic boundary condition. Sorry, what? Yeah, right. Yes, right. Yeah, I will explain this one later. Yeah. But what I'm trying to say, purely from the gauge theory side, we cannot find out how much states, how many states we need to subtract. So in the following, I will use some techniques from the representation theory to find out this number.
Don't you can turn on massive? This is massive.
Yeah. But indeed, when you turn on the test parameter, but actually but when theta goes to 0, there's no, well, it's, I mean, the scalar potential, if we just, depending on the, how to say, yeah, I also turn off the Fi parameter and the theta. This is on the singular point. Yeah. Depending on when we turn on the twist masses, right? If we go to the single point directly and then tuning on this twist mass, I think. Yeah, we indeed turn on the twist mass. Yeah. But the only thing I can say is when theta is non-zero, that's indeed you only left with discrete vacuum. But we are talking about when go to the singular point, and we actually find out. Okay, so I can talk about a little bit more about the numerical result. When we find out the solution to the Bethe equation and tuning this theta go to 0, you will find out some vacuum will go to infinity. Yeah, that's what we mean by flow go to the infinity. It's escape from the finite region. Yeah. Okay, let me use two examples. The one example is the SU2 of length 2. This is an example we already know in the quantum mechanics class. So what we find out is in the previous fully twisted case, it's this number, the CSLM. And if in this example, we can compute this as L choose M. And however, when you turn off this theta angle, you will restore the SU2 global symmetry. And all the physical states are these high-sway states, which I circled by this red circle. I use the red circle to emphasize the high-sway states. And this green ones, the states in the green circles are the descendant states we need to extract, need to subtract. And this number of these states in the green circle are exactly this number we need to subtract. And this is another example is SU2 of length 3. And you will find out you need to subtract this green, the states in the green circles, and which matches this this number. Yeah. Okay. Okay. Here comes our main result. Based on the previous observation, we find out we can actually use this formula. We call it the difference formula, which is we apply this D, which called the shift operator determined by this polynomial. We apply this different shift operator on this CSLM will give you this this number, which called mu lambda. This mu lambda is actually the number of physical Bethe states when all theta goes to 0. And this R of t is actually the wire denominator of this SUR plus 1. We have given this, we are writing a paper to prove this based on wire character, and we will post this very soon. Okay. So you may recognize that okay. Oh, this is a definition of the shift operator. We can define a shift operator associated to any polynomial p here. We can apply this this shift operator on this any function of fm, which is defined by this one. We just expand this p with each term takes form like t1 to the beta 1 product until the tr beta r. And you shift this by beta, this amount. Sorry, P. Oh, P is a polynomial. For example, in this result, we need to expand this product to get a polynomial like P of T. So we just, yeah, this is just the wire denominator. There's another way of writing this one by sum of the wire group. Yeah, and I will show explicitly what this formula, this expression means. In this case, it's SUR plus 1. The AR. Yeah, A type. This little r is the rank of the gauge group. Oh, sorry, not the gauge group, sorry, the globe symmetry. Yeah. L is a number of side, spin side. S is the spin. R, this little r. Little r is the rank of the global symmetry. Oh no, that is a global symmetry for the spin chain, not the global symmetry for the gauge theory. Yeah. No, it's corresponding to the. If you view the quiver gauge theory as a Dunking diagram, it's like if you have two gauge knots, that's A2. Oh, this one is this one. You have R nodes. So, yeah. Sorry, what?
At least one of the previous slides.
Oh, previous one. Oh, this is an example of SU2 of length 3.
I thought you were looking at XXX.
Yeah, XXX, yeah.
Yeah, which corresponds to SUM. We go and gauge theory with delta.
Yes.
Which is
But-
not that.
Yeah, we generalize to the linear quiver case in the previous one. For example, like yeah, this one.
Oh,
Yeah, this one is the most general one we are considering. Okay. Okay. So you may realize that this is actually it's a very classical problem in the representation theory. We are basically dealing with the tensor product and the tensor powers of this representation and decompose into irreducible representation. And this mu is actually the multiplicity of this irreducible representation in appearing in this decomposition. And so in this sense, we give a difference formula for compute this multiplicity mu lambda. More specifically, the previous formula can be, in this case, can be explicitly written like this one. You can see this, the previous numerical results agree with this. It's a kind of a alternating sum, but it's actually signed by this sign of omega. This omega is a Weyl group of this AR. Okay. So far we can say we also have some numeric result, numerical test of verify this result, and also we have given a fully rigorous proof for this one. It's yeah. So that's for the periodic spin chain. However, the story is not over yet. Let me skip this part. And we can actually consider other cases of a very boundary condition in the middle of this fully twisted case and also fully the global symmetry is fully restored case. So let me start with a discussion of this global symmetry and boundary conditions. Okay, quiver. This one. Yeah, just no. I just have this this L. No. Yeah, in principle, yeah. Oh, because the motivation is to consider the spin chain like this SU R plus one. Yeah, but indeed there are some more general cases with, but we haven't dealt with that. Yeah. Okay. Okay, so let me start with a discussion with the relation between global symmetry and the boundary conditions. This is more, it's more easier to study this one by algebra Bethe knots. And we actually modify this previous discussion by adding this twist boundary condition with the phase matrix with the only diagonal. We denote it as phi I, where and the phi I and are related with the thetas by the theta I is phi I minus phi I plus 1. And here the T is a monodromy matrix satisfy this RTT relation. Okay, and basically we want to discuss the most general cases of this phase type of phase matrix, and we want to find out all the corresponding Bethe states that are spaceway states respect to subgroup symmetry after we take a specific choices of this phase. So if we can see this global symmetry by expanding this monodromy matrix in terms of U expansion, and because the first term is this subneeding term corresponding to the generators of this global symmetry, and basically if these generators commute with the transform matrix, that means it's we should include this as a generator in global symmetry. And we find out the commutator with the commutator between little t, this transform matrix, and this global symmetry generators is given by this much. So that means when certain this phase satisfy when this phase equal to 0, we need to include this as a generator. We need to include this into the global symmetry generators. Okay, let me to be more specific. If you for each pair of I equals not equal to ij, if remember the theta, sorry, remember the theta I is equal to phi I minus phi I plus 1. So whenever whenever this equation happens, we will find out that there must be this factor goes to 0. That means we need to include this one. And this condition actually consider we should include the positive roots like this one. Sorry, there's a typo. We don't need to include take this to 0. So which means if we take the boundary conditions with theta angle satisfy this condition, we need to include the positive roots like alpha I plus 1 until alpha j minus 1. Okay, so most basically, this theta? Oh yeah, this little t, yeah. But this little t with we insert this phase inside. Yeah. Okay. Here is an example. There are various boundary conditions for the SU3 cases. if we draw the diagram parameterized by this theta 1, theta 2, in the most generic one, where theta 1 and theta 2 are all non-zero, that corresponding to the global symmetry is U1, because the diagonal always commute with this transfer matrix. And if we take the theta 1 equal to 0, that means we get this line. Actually, you will find out the global symmetry will be U1 times SU2. Similarly, on this line, you will also have the global symmetry U1 times SU2. And in the line of theta 1 plus theta 2 equal to 0, similarly, you have this global symmetry. However, I should emphasize, even though they have the same global symmetry, but you will find out the multiplicity will be different because we have different generators appearing. It's a different embedding structure of this subgroup into SU3. And when theta 1 equal to theta 2 equal to 0, that is a periodical case, as we discussed before, SU3. Okay. Here's a more discussion about the SU4. You can find out there are various boundary conditions with corresponding to various global symmetry. You will find out. Okay. So here's a quick summary. We have discussed this subgroup symmetry has a one-to-one corresponding to the twist boundary condition. And actually, we can interpret this correspondence by choosing certain positive roots, as we discussed. So that positive roots appearing, if you remember the difference formula we proposed, that positive roots appearing in the polynomial determining this shift operator. So in the spin chain with this partial global symmetry, we can actually we propose this similar difference formula, but by changing this polynomial with which is determined by this positive roots, and we can actually prove this formula, and in the upcoming paper. And this, I should say, this H is a sub-Lie algebra determined by this subset of these positive roots. Okay, and let me explain a little bit about what we are talking about. So if we, for example, if we choose a subset of positives like this one, alpha 2 plus alpha 3 and alpha 4, of course we also need to add another one to make it sub-algebra, which is alpha 2 minus plus alpha 3 plus alpha 4. And if we have this choice, we basically consider restricted representation, and which means we need to pick up a certain rules from the original Young diagram and then gluing them together. This is finally the restricted representation for the sub-algebra. And I should make a remark that the unpicked rows actually correspond to the residual U1 charges. And this is a final example. So previously we calculated the Foley twist case, which is a CSLM with M1, M2. This is given by this product of binomial. And in this example, SU3, we have four cases. The extreme one is when all the twist boundary condition, all twist parameters are non-zero, you get the Foley twisted case. While you pick alpha 1, alpha 2, you can get SU2, and also alpha 1 plus alpha 2. Here I only list one example, which is equivalent to pick this top left corner. And we can actually consider the multiplicity by using the formula we proposed before. And this agree with numerical test as well. And I should emphasize that even though here the Young diagram actually we are using is a redundant Young diagram. That means, for example, this diagram is equivalent to this diagram by eliminating the first column. And however, if you detailed study the structure of embedding we find out that this Young diagram, even though this Young diagram is equivalent to this Young diagram, however, they correspond to different sorts of the embedding structure. So we write it in different way. So okay, here let me conclusion. So we proposed a new formula for tensor product multiplicities, including the branching rule, which counts the Bethe states in the XS spin chain in various diagonal twisted spin chains. And actually, I should emphasize that our formula will apply to A-type super spin chains. Rick's proof is still missing, but we will work on that. And there are some generation of this one, for example, other type groups and introducing impurities. And also, how about the quantum groups? We will also consider that. And actually, there's a hint for the dual gauge theory on the singular loci. For example, in 2022, there's a paper by Wei Gu. He mentioned that on the singular point, there might be a R-symmetry enhancement. But that R-symmetry should, for example, in the XX spin chain, the R-symmetry enhancement will from U1 enhance to SU2. That corresponds to the global symmetry of the spin chain. But more detailed studies should be conducted. Yeah. Thank you.
Are there any questions? Well, I have a question. Can you describe somehow how to generalize this work to, for example, XXZ spin chain?
For the XXZ, so far we only started a little bit because XXZ only has U1 symmetry, but it also has some quantum group. But that only appears in the open spin chain. But so we first want to generalize to spin chain with open boundary conditions, and then look at how this works on the XXZ spin chain.
So what are the main difficulties in this generalization to XXZ? Is that mathematical or physical?
Physical, mathematical. I think mathematical. What do you mean by physical difficult?
Just do we lack some physical intuition in this generalization?
Sorry, what?
So do you have some physical intuition that guides us to this generalization to XXZ?
Physical intuition. Okay. From my point of view, I want to study the 3D gauge theory and to see how this story applies there. Yeah. That's all my motivation. Yeah.
Okay, thank you.
Maybe I'll ask once again what I asked earlier. So what about the cancellations between ground states in the index? You said that you don't have them here, right?
Yeah.
So all the ground states are bosonic.
Yeah.
Is there a reason for that?
I don't have a clear reason, but that's all we compute. The result matches.
But you can actually count those ground states just combinatorially without reference to index, right? You can just count.
You mean geometrically?
Well, geometrically, or you count those Young diagrams.
Yeah.
Was index actually important for anything?
Okay.
Or you used it to get the formula?
Yeah, I use the form to get the combinatorial sorry, I use that computation algorithm to get the combinatorial problem, which we are able to use. We are able to get the more general result.
And then you check that that formula matches with the number of diagrams, so
Yes.
that there are no cancellations.
Yeah.
Any more questions? If there are no questions, then let's thank the speaker again.
Okay.